The internal combustion engine works on the sequence of separate processes: intake, compression, combustion, expansion, and exhaust. It does not operate on any thermodynamic cycle because it involves an open system. The working fluid is fuel and air mixture, enters into the system in intake stroke and leaves it in exhaust stroke. So it does not complete a cyclic process. So to analyze the performance of engine, it is idealized as the closed cycle in which only air is working fluid and heat is supplied by the reservoir. This standard cycle is known as air standard cycle. Air standard cycles are idealized cycles based on the following assumptions. The working fluid is air, that is ideal gas. All the processes are internally reversible. Combustion process is replaced by heat input from an external source. Heat rejection is used to restore working fluid to its original state. Intake and exhaust process are not considered. Engine friction and heat loss are not considered. Specific heat is independent of temperature. This image shows the actual engine process and Otto cycle process. Now let us derive the relation for Otto cycle efficiency. In Otto cycle, 1 to 2 is isentropic compression, 2 to 3 is constant volume heat addition, 3 to 4 is isentropic expansion, 4 to 1 is constant volume heat rejection. In Otto cycle, the combustion is so rapid that the piston does not move during the process, and therefore the combustion is assumed to take place at constant volume. From the definition we have already discussed earlier, compression ratio R is equal to V1 by V2 and also equal to V4 by V3. Cutoff ratio RC is equal to V3 by V2. Expansion ratio RE is equal to V4 by V3. In Otto cycle, compression ratio and expansion ratio are equal, whereas in diesel cycle they are not equal. Otto cycle efficiency, neta is equal to net work done by heat input given. This can also be written as 1 minus Q out by Q in, that is equal to 1 minus T4 minus T1 by T3 minus T2, that is equal to 1 minus T1 of T4 by T1 minus 1, T2 of T3 by T2 minus 1. For isentropic process, PV power K is equal to constant, where K is equal to Cp by Cv, which are specific heats at constant pressure and constant volume respectively. For process 1 to 2, we know P1 V1 whole power K is equal to P2 V2 whole power K, which can also be manipulated as V1 whole power K by V2 whole power K is equal to P2 by P1. From ideal gas formula, RT2 by V2 RT1 by V1, that is equal to T2 by T1 into V1 by V2. V1 whole power K by V2 whole power K into V2 by V1, that is equal to T2 by T1, which can be further simplified as T2 by T1 is equal to V1 by V2 whole power K minus 1, that is equal to volume at BDC by volume at TDC whole power K minus 1, that is equal to compression ratio whole power K minus 1. For process 1 to 3, T3 by T4 is equal to V4 by V3 whole power K minus 1, that is equal to volume at BDC by volume at TDC whole power K minus 1, that is equal to half R power K minus 1. Then T2 by T1 is equal to T3 by T4 or T3 by T2 is equal to T4 by T1. Then efficiency is 1 minus 1 by R power K minus 1. Effect of compression ratio on efficiency is shown here. You can clearly see that efficiency increases with increase in compression ratio, but there are some problems associated with higher compression ratios. As you increase compression ratio, temperature of air fuel mixture increases and auto ignites, which is called knocking. With knocking, initial ignition of mixture is initiated by spark plug. Due to combustion pressure and induced heat, a spontaneous combustion of mixture occurs. A second, almost parallel combustion inside the cylinder will occur when the both flame fans hit with intense high frequency waves are produced. The pressure waves create the characteristic metallic ping sound and cylinder pressure increases dramatically. Knocking combustion can lead to pre-ignition also. A glowing spot somewhere in the chamber is the most likely point for pre-ignition to occur. For example, a carbon ember can ignite the charge while piston is very early in compression stroke. Next, let us discuss CI engine versus thermodynamic diesel cycle and derive relation for efficiency. 1 to 2 is isentropic compression and 2 to 3 is constant pressure heat addition, 3 to 4 is isentropic expansion, 4 to 1 is constant volume heat rejection. Due to ignition delay and finite time required for fuel injection, combustion process continues till the beginning of power stroke. This keeps the cylinder pressure at peak levels for a longer period. Therefore, the combustion process can be approximated as constant pressure heat addition. Compression ratio R is equal to V1 by V2, also equal to V4 by V3, and cutoff ratio RC is equal to V3 by V2, and expansion ratio RE is equal to V4 by V3. Diesel cycle efficiency neta is equal to net work done by heat input given, which can also be written as 1 minus Q out by Q in. Neta is equal to 1 minus Cv into T4 minus T1 by Cp into T3 minus T2. That is equal to 1 minus T4 minus T1 by K into T3 minus T2. That is equal to 1 minus T1 of T4 by T1 minus T1, T2K, T3 by T2 minus T2. For isentropic process 1 to 2, T1 by T2 is equal to V2 by V1 whole power K minus 1. For isentropic process 3 to 4, T3 by T4 is equal to V4 by V3 whole power K minus 1, which can also be written as V1 by V3 whole power K minus 1, which can also be simplified as shown. And similarly, for constant pressure process 2 to 3, Pt is equal to P3. We know ideal gas law, RT2 by V2 is equal to RT3 by V3. So, T3 by T2 is equal to V3 by V2, that is equal to RC. Then efficiency 1 minus 1 by R power K minus 1 into RC whole power K minus 1 by K into RC minus 1. Since RC whole power K minus 1 by K into RC minus 1 is greater than or equal to 1 for a given R, efficiency of diesel cycle is always less than Otto cycle for a given R. But usually diesel engines have higher compression ratios, so they are more efficient than petrol engines for a given capacity.